In engineering mathematics, we often meet differential equations that describe how a physical quantity changes with time or space. When the equation is linear, the unknown function and its derivatives appear only to the first power and are not multiplied together, and the coefficients do not depend on the independent variable. We can write it in a very tidy standard form. A sub ny to the n plus a sub n minus 1 y to the n minus 1 plus plus a sub 2 y double prime plus a sub 1 y prime plus a sub 0 y equals 0, where each a sub k is a real constant, and y to the k denotes the kth derivative of y with respect to x or t. Think of the left-hand side as a weighted sum of the function and its successive rates of change, much like a stack of springs and dampers in a mechanical system where each spring constant is fixed, though a sub k. The highest derivative y to the n determines the order of the equation. An nth order model can store n independent pieces of initial information, for example position, velocity, acceleration, and so on. Explanation. To solve the homogeneous equation, we replace y by an exponential trial, y equals e to the rx, because the derivative of an exponential is proportional to itself. Substituting y equals e to the rx into the standard form gives a polynomial equation in the unknown r. A nr to the n plus, a n minus 1r to the n minus 1 plus plus a 1r plus a 0 equals 0. This polynomial is called the characteristic or auxiliary equation. Its roots dictate the shape of the solution. As an example, for y triple prime minus 6y double prime plus 11y prime minus 6y equals 0. The characteristic equation is r cubed minus 6r squared plus 11r minus 6 equals 0. And factoring yields r minus 1, r minus 2, r minus 3 equals 0. So the roots are r equals 1, 2, 3. Each distinct real root will generate a simple exponential term in the final solution. If a root repeats or appears as a complex pair, we must treat it differently. See the next three topics. Explanation. When the characteristic equation has n different real roots r1, r2, rn, the complementary homogeneous solution is simply a linear combination of exponentials. Y sub c of x equals c1 e to the r1x plus c2 e to the r2x plus cn e to the rnx. c1 through cn are arbitrary constants fixed by initial or boundary conditions. For instance, solve y double prime minus 5y prime plus 6y equals 0. The characteristic equation r squared minus 5r plus 6 equals 0 factors as r minus 2 times r minus 3 equals 0, giving r1 equals 2, r2 equals 3. Well, hence, y sub c of x equals c1 e to the 2x plus c2 e to the 3x. In a physical context, imagine a circuit with two independent decay modes. One dies out quickly at rate 3 and the other more slowly at rate 2. The overall voltage is just the sum of the two decays. The same idea works for any order as long as the roots stay distinct and real. If a real root r appears more than once, the simple exponential e to the rx is not enough to generate the required number of independent solutions. The theory of linear ordinary differential equations tells us to multiply by powers of x to create new linearly independent terms. For a double root r, we get y sub c of x equals c1 plus c2x times e to the rx. For a triple root, we would add c3x squared times e to the rx, and so on. Y double prime minus 4y prime plus 4y equals 0. The characteristic equation r squared minus 4r plus 4 equals 0 simplifies to r minus 2 squared equals 0. So r equals 2 is a double root. Consequently, y sub c of x equals c1 plus c2x times e to the 2x. A practical analogy is a mass spring damper system tuned exactly to its natural frequency. The displacement then grows linearly in time multiplied by the usual sinusoid, reflecting the repeated root in the governing equation. The extra factor x, or x squared, guarantees we have enough independent pieces to satisfy the required initial data. When the characteristic polynomial yields a pair of complex conjugate roots r equals alpha plus or minus I beta, the corresponding exponentials e to the alpha plus or minus I beta times x can be rewritten using Euler's formula into real sines and cosines. y sub c of x equals e to the alpha x times c1 cos beta x plus c2 sin beta x. Here e to the alpha x determines the exponential growth when alpha is greater than 0 or decay when alpha is less than 0, while the sinusoidal part describes oscillations with angular frequency beta. Example, y double prime plus 4y equals 0. The characteristic equation r squared plus 4 equals 0 gives r equals plus or minus 2i, so alpha equals 0, beta equals 2. Therefore y sub c of x equals c1 cos 2x plus c2 sin 2x, which is exactly the motion of an ideal undamped spring mass system, vibrating at frequency 2 radians per second. In engineering, this case appears whenever a system is underdamped, producing decaying oscillations if alpha is negative. Complex root solutions are always real combinations of exponentials and trigonometric functions, so they fit physical measurements that are real valued. When the differential equation is non-homogeneous, meaning it has a right-hand side f of x, we need a particular integral y sub p that satisfies the full equation. The method of undetermined coefficients works well when f of x is a linear combination of polynomials, exponentials, sines or cosines or products of these. The idea is to guess a form for y sub p that mirrors f of x, insert it into the ordinary differential equation, and solve for the unknown coefficients. Typical trial forms. If f of x equals p sub m of x, a polynomial of degree m, guess y sub p equals x to the s times open parenthesis a sub mx to the m plus dot 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 plus a sub 0 close parenthesis. If f of x equals e to the lambda x, guess y sub p equals x to the s times open parenthesis b e to the lambda x close parenthesis. If f of x equals sin omega x or cos omega x, guess y sub p equals x to the s times open parenthesis c cos omega x plus d sin omega x close parenthesis. The exponent s is 0 unless the guessed form duplicates any term already present in the complementary solution. In that case, we increase s by 1 or more to preserve linear independence. Example, y double prime minus 3y prime plus 2y equals e to the x. The characteristic equation r squared minus 3r plus 2 equals 0 gives roots r equals 1 and 2. So the complementary part is y sub c equals c sub 1 e to the x plus c sub 2 e to the 2x. Because e to the x already appears in y sub c, we must multiply the usual trial a e to the x by x to avoid duplication. Try y sub p equals a x e to the x. Compute derivatives. Y sub p prime equals a e to the x plus a x e to the x, and y sub p double prime equals 2 a e to the x plus a x e to the x. Plug into the ordinary differential equation. Open parenthesis 2 a e to the x plus a x e to the x close parenthesis minus 3 open parenthesis a e to the x plus a x e to the x close parenthesis plus 2 open parenthesis a x e to the x close parenthesis equals e to the x. Simplify, open parenthesis 2 a minus 3 a close parenthesis e to the x equals negative a e to the x equals e to the x, so a equals negative 1. Hence y sub p equals negative x e to the x. The full solution is y equals c sub 1 e to the x plus c sub 2 e to the 2x minus x e to the x. This technique is quick for engineering problems where the forcing function is a simple, regular signal. For example, a steady voltage, a sinusoidal load, or a polynomial load. Explanation: when f of x is not of the simple types handled by undetermined coefficients. For example, f of x equals sec x, ln x, or a product of mismatched functions, we use variation of parameters. The method works for any linear ode of order n. First, we find the complementary solution y sub c equals sum from k equals 1 to n of c sub k times y sub k of x, where the set of y sub k are linearly independent solutions of the homogeneous equation. Then we allow the constant c sub k to become functions u sub k of x, and write a trial solution y sub p of x equals sum from k equals 1 to n of u sub k of x times y sub k of x. Impose the auxiliary conditions. Sum from k equals 1 to n of u sub k prime of x times y sub k to the jth derivative of x equals 0, for j equals 0, 1, up to n minus 2. This simplifies the algebra when differentiating y sub p. Substituting y sub p and its derivatives into the original ode yields a single equation for the remaining unknowns. Sum from k equals 1 to n of u sub k prime of x times y sub k to the n minus 1 th derivative of x equals f of x. This linear system for u sub k prime of x can be solved using Cramer's rule. The denominators involve the Wronskian w of y sub 1 through y sub n. Finally, integrate u sub k prime of x to obtain u sub k of x and thus y sub p. Example third order ode, y triple prime minus y equals sec x. Step 1. Solve the homogeneous part. Characteristic equation r cubed minus 1 equals 0 gives r equals 1, and r equals negative 1/2 plus or minus I times square root of 3 over 2. Hence y sub 1 equals e to the x, y sub 2 equals e to the negative 1/2 x times cosine of square root of 3 over 2x, and y sub 3 equals e to the negative 1/2 x times sine of square root of 3 over 2x. Step 2. Compute the Wronskian w, a non-zero expression. Step 3. Set up the system for u sub 1 prime, u sub 2 prime, u sub 3 prime using the auxiliary conditions. After simplification, one finds u sub 1 prime equals sec x times w sub 1 divided by w, u sub 2 prime equals sec x times w sub 2 divided by w, and u sub 3 prime equals sec x times w sub 3 divided by w, where w sub k are determinants obtained by replacing the kth column of w with the vector 0, 0, sec x. Integrating these gives u sub k of x. The resulting particular integral is messy but completely determined. Adding it to y sub c yields the full solution. In practice, engineers often turn to computational tools for the integration step, but the underlying idea, letting the constants vary to accommodate a complicated forcing term, remains fundamental. An initial value problem, IVP, asks for the specific solution that satisfies prescribed values of the function and its first n-1 derivatives at a point, usually x equals 0. Because an nth order linear ordinary differential equation has n arbitrary constants, the initial value problem uniquely determines them. Example, solve y fourth derivative minus 2y double prime plus y equals 0, with y of 0 equals 1, y prime of 0 equals 0, y double prime of 0 equals 2, y triple prime of 0 equals 0. Characteristic equation, r to the fourth minus 2r squared plus 1 equals 0, which factors to open parenthesis r squared minus 1 close parenthesis squared equals 0, so r equals plus or minus 1, each is a double root. Build the complementary solution using the repeated root rule. Y sub c equals open parenthesis c1 plus c2x close parenthesis e to the x plus open parenthesis c3 plus c4x close parenthesis e to the negative x. Differentiate to obtain y prime, y double prime, y triple prime and evaluate at x equals 0. Y of 0 equals c1 plus c3 equals 1. Y prime of 0 equals c1 plus c2 minus c3 minus c4 equals 0. Y double prime of 0 equals c1 plus 2c2 plus c3 minus 2c4 equals 2. Y triple prime of 0 equals c1 plus 3c2 minus c3 plus 3c4 equals 0. Solve the linear system for c1, c2, c3, c4. From c1 plus c3 equals 1, equation 1. c1 minus c3 plus c2 minus c4 equals 0, equation 2. c1 plus c3 plus 2c2 minus 2c4 equals 2, equation 3. c1 minus c3 plus 3c2 plus 3c4 equals 0, equation 4. Solving gives c1 equals 3 halves, c2 equals 1 half, c3 equals negative 1 half, c4 equals 1 half. Substitute back. Y of x equals open parenthesis 3 halves plus 1 half x close parenthesis e to the x plus open parenthesis negative 1 half plus 1 half x close parenthesis e to the negative x. This function satisfies the differential equation and all four initial conditions. In exam settings, the workflow is 1. Write the standard form. 2. Find the characteristic polynomial. 3. Compute roots and construct y sub c. 4. Apply the initial value problem to determine constants. And 5. Write the final answer clearly. The same steps apply to lower order problems, merely with fewer constants. Real-world analogies. The initial value problem is like a car whose position, speed, acceleration, and jerk are all measured at time 0. The ordinary differential equation models the dynamics, and solving the initial value problem tells you exactly how the car will move thereafter.